All right, welcome to video 3 in the regression modeling series. This one hopefully will be pretty short. We're going to go through to using the geographically weighted regression tool and using the spatial autocorrelation tool again and what you're looking for this time. So to start off with, we now have all of our variables that pass. So in this case, we have percentage of adults that report smoking, BMI value of 30, percentage food insecure, houses with overcrowding, houses with lacking kitchen or plumbing facilities, and non-native English speakers who are not proficient in English. So those are the variables we're going to run with our geographically weighted regression. So let's go ahead and find that. Keep in mind we are going to run this one twice because we need to run it first using the golden search to find our ideal number of neighbors, and then we need to run it again when we know what our ideal number of neighbors is. So for the dependent variable, get our poor mental health, go ahead and select all, and then uncheck the ones that don't work. So that one is gone. Those two, oh, that one obviously is gone. That's our dependent variable. Those two are good. That one's gone. That's good, 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 gone, gone. Oh, that one's good. And then don't forget to get rid of your shape length and shape area just to check that is 6 variables, and we have 6 variables. So just like our regular naming, we're just going to call this GWR1. Our neighborhood type for the first one is going to be number of neighbors using the golden search, and our values are going to be between 10 and 200. So you go ahead and run this, and you do get this output or something similar. And you'll see that this one is much more random than the previous one. So here's our generalized linear. You can still see some of those states. Less so in this one, still a little bit defined, but we also aren't fully finished with our model yet. So when you use the golden search, you get this report. And the first thing it does is it shows you your golden search results and your AICC. Keep in mind you're looking for the lowest number here. So obviously 10 is not a good choice. But if we look through, you should find that 96, I believe, or 95 is the lowest. So 6470. 6634 is lower than that. Yes, so 6634 is the lowest number we are seeing here. So we would use 154 neighbors for this example. So then you run your geographically weighted regression again. All you have to do is change this to 2 for your name, keep number of neighbors the same, and then just change your golden search to user defined and type in whatever number is the lowest, in this case 154. You will then get a second output chart, not very different than the last one, a little bit better. Okay, you will get this report. Things always dock so strangely. So again, that ideal number of neighbors, 154, all the variables passed, and you do get that adjusted R squared of 0.91, so you will need to write that down. So for your final product for the geographically weighted regression, you need to report the golden search value, so 154 as the number of neighbors, the adjusted R squared of 0.9156, and your map of standard residuals, so you will then export the map behind. And then the last part for this part of the project with the geographically weighted regression is we do need to run that spatial autocorrelation one more time. So your input, again, this time is the GWR that passed, and your input field is your standard residuals. We do want to generate a report. This time, instead of using inverse distance, we're going to use k nearest neighbors since that's what we've been using. And instead of 8, we're going to use 154. So you go ahead and run that. Remember, again, you don't get a map this time, you just get a report. Like so. And when you open the report file, you will see that you have a hopefully random distribution and a p-value and a z-score that are within range. So at this point, we can be assured that our model is spatially random. And that's it for video 3.